let's get this shown. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Let's just jump right into it. What's to talk about today? People still trickling in here. Let's see. All right, so before we begin, want to talk about tomorrow, which, as you know, is the date for the first test. Kind of talk about the general plan there, as well as some things that I posted. So, seems like people are still trickling in, you know. Yeah, okay, so I'll talk about the general plan, and then I'll take questions if you guys have any questions. And if not, we're just going to continue with the lesson. So some things to note. Some things to note here is one, we have 5 practice problem sets have been posted. Not getting my hand on very stable here, writing very choppy. The 5 practice problem sets posted. Probably I should mention on a grade scope. All except the first are timed. I think one is timed for like 60 minutes and the others are timed for like 75 minutes. But, you know, when you log in, you'll know which is which because it'll be in the instructions. So I would say don't open the timed ones until you know, all right, I can reserve this much time to actually just do it one shot. That's going to be the closest to the test. So you can just sit down, finish everything all in one shot. Let's see here. Still trickling in. So don't start them until you can complete them. What else did I want to say? So the, you know, as you guys know, it's summer, everything is compressed. Trying to finish a course in a little more than a quarter of the time isn't easy. So obviously you guys know it's intense and there's a lot to do. So at least for the first test, kind of want to give you some time to, I guess, get acclimated to some things. And I have like 5 practice tests. I want to make sure you have enough time to actually go through them. So I've decided to give you a window for the exam. So you would have more time to practice if you actually need it. I can't promise this towards the end when we're around test 2 and the final, because there's like a deadline to grade by. So I'll be a little bit stricter there. But say for the first test, I mean, I give you Thursday, I'm not going to grade it until the weekend anyway. So I think I can actually push that a little bit. And so that's what I will do. So I'm thinking of making the test Now the test itself is still timed. Like, so once you open the test, it will be timed, but you have a window in which you can start the test. So let me actually talk about that. So test 1, it is going to be, yeah, I think an hour, it's 75 minutes long, around there. It will begin or let me say, it will be open from, when is our actual test day? I think that's the 21st. Yes. So July 21st, 2022 at, I think I can start around, let's say 3 p.m. to July 22nd, 2022. And I'll start that around 9 p.m. So that's probably when I want to start grading, like Friday night maybe. So you'll have that window, right? So let's say tomorrow comes, you still feel a little shaky, you want to look over something some more, you can sleep on it another night and just try to finish it early on Friday. So definitely you'll want to begin test 1 by around, latest worst case scenario, like 7 p.m. on Friday. You don't want to push it later than that. But yeah, so you'll have that window. But it's important that you know, once you click 75 minutes long from time of opening, once you click on it, the time has begun. Can't reset. You just have to finish it right there. And that's the same thing with all the quizzes, all the practice problem sets, other than the first one. The first one, I just left it open because I just want that one. I want you to be able to just see what it's like in Gradescope. You go in, you go out, you think about stuff, you play around with things, troubleshoot any issues. Like the first practice test that's the one where you kind of realize, oh, I don't know how to upload things quickly. So let me just keep figuring out troubleshooting ways to upload quickly. Or, oh, I realize I don't know how to use this function or that function. And this is your chance to figure out. So you can actually use the first practice test in that manner to just kind of not only review the topics, but also kind of get used to using Gradescope. If you know you're going to want to log in from your phone as well to take pictures and upload quickly, make sure you actually test that on that one. And then you just want to know what you're doing. But yeah, so all of that. So by the time you actually do the first test or you open the first test, you're aware of everything that you have to do. You know you're going to be in a spot with good internet access. You know how to upload things quickly, and you'll know how to go around Gradescope, how to open a test, how to do all that. But for the actual test, I'll give you a window, a little bit more than 24 hours to actually complete it in. That being said, then, since I'm giving you this window, tomorrow I'm just going to continue. I'm going to have class. I'd rather kind of rush now as opposed to rushing towards the end. So if we finish early, that would be nice. And I can maybe even do a review for the final. So since you have this window, I'll continue with regular class tomorrow. Now, for those of you who do not decide that, you know what, I'm going to just take that extra day and I know I'm going to do it on Friday, I might have like a mini Q&A session / review, say the last hour of tomorrow's class. Okay, so tomorrow I'll teach for the first 2 hours, and then in the last hour, if you guys have questions from some of the practice tests that you've been trying, I can actually answer those. And that being said, I think I did extend the deadline for the practice tests as well, just to give you some more time. So I think the practice tests, they all close 6 p.m. on the Friday. And then, the actual test closes at 9 p.m. what else do I want to say? Oh, I wouldn't do something like do a practice test and then right away go into the actual test, right? You kind of want to be relatively fresh, right? And rested and all that. So you don't like do anything, don't cram back to back. You know, you have 5 practice tests. Now you have a couple days to do it. Space them out, you know, do 2 here, do 1 there, do another 2 here. And so you kind of sit comfortably for the first test. So yeah, test 1, I think that's all the important points. So yeah, make sure you can log into Gradescope, make sure you can use Gradescope, and that will keep you. And once you cover the practice test, you'll see all the kinds of questions that I would ask, all the kinds of ways that you might have to show your work, etc. And so you should be pretty comfortable after going through all of those. So that being said, are there any questions, comments, or concerns about any of this? Okay, well,
I have a question just to make it clear.
Mhm.
So it doesn't matter if we open it on July 21st or 22nd.
Correct.
The moment we open it, we just have 75 minutes from that, right?
Right. As long as you finish it before 9 p.m. So at
Friday.
9 p.m. on Friday, no matter where
Okay.
you are, it's going to kick you out. So you want to start, you know,
Ahead.
before
Okay.
that.
Yeah, that makes sense.
So you definitely don't want to start after like 7:45 on Friday. So I would just say,
Yeah.
just if you want to like last minute, like give yourself as much time, I would say you need to start by like 7 p.m. on Friday, the latest.
Okay.
But you can do it as early. If you reviewed everything, you're totally comfortable. You're like, yeah, man, I got this. You can do it 3 p.m. tomorrow. And,
Okay.
and you just come to class and chill. But
Okay.
otherwise,
Just to make
yeah.
just to make it clear, like, what if we need some extra time to upload the pictures and everything? Will it just kick us out, or?
Yeah, it'll close at that point. The 75
Okay.
minutes will include upload time.
All right. Perfect. All right. Thank you.
Yeah.
That was about
And
it.
so that's why I definitely want you to practice with the other thing, because especially if you're using your phone and taking pictures, uploading should not take a long time. You can literally, you
Right.
write out your answers, you take a picture and you upload on your phone. While your phone is like uploading, you can move on to another problem.
Right.
So you can even be uploading technically while you're doing the test, right? Every time you do a problem, you just take a picture of it, upload, move on to the next problem, take a picture of it, upload, move on to the next problem. So it shouldn't take that much time. I might add a 5-minute cushion, so maybe time it for 80 minutes or something like that, but you really shouldn't need longer than that, provided
Right.
that
Thank you
you're
so
doing.
much.
Okay,
Thanks.
so yeah, so that's how we're going to do test 1, give you a little bit of a window and a cushion. Like I said, I can't promise this for like test 2 or the final, because then everyone's going to be cramming, including myself, to kind of get everything finished in time. But for test 1, I think that's the protocol. Other than that, the instructions are going to be very similar to the instructions that you see on the practice exams. So if you read the instructions on the practice exams, you probably can skip reading the instructions on the actual test. But just make sure you follow the instructions. Other than that, I think, yeah, any other questions? Yeah, so someone said relatively how long it was yesterday. So you can expect 15 to 20 problems, but not all of those are ones they have to write out. There are going to be some concept ones, some multiple choice, some select all that apply, and maybe a little more than half of those is stuff where you have to actually show your work. So it'll be 15 to 20 problems, depending on how much concepts I want to ask. I have like a template I want to use for the test already, but I don't know if I'm going to include other stuff or maybe take away some stuff. So I don't really know exactly, but expect to be around there. So expect you're going to solve somewhere between 8 and 12 problems you're going to have to write out and take your pictures. And the rest is going to be like short answer, fill in the blank, multiple choice, etc., that kind of thing. So yeah, so that's the important thing for tomorrow. And like I said, tomorrow I will continue. I'll just continue with lectures, but like the last hour or so, I will just, I'll give you guys the option of, hey, if you want to ask me questions about, something that you found confusing in the practice tests or anything like that, I'll answer questions now. We might even be able to do specific problems from the practice tests if you feel that will help you. And if not, I can continue after that, but I'll give you guys the option for that tomorrow. So that being said, let's actually jump back into it. Let's talk about what we spoke about yesterday. So yesterday we just finished up improper integrals. And we did two other examples where we're using the comparison test. And we saw an example where the direct comparison test worked, but if you were to do something like the limit comparison test, it would not have worked. And again, it involved a trig function where just understanding how to bound them is very useful. So we know that secant of x is always greater than or equal to 1. And that's something you can, secant of x is always either greater than or equal to 1 or less than or equal to -1, but secant squared, obviously the positive part is going to be greater than or equal to 1. And we actually could use that to our advantage here. We also saw something like this, where it comes down to sometimes you have an improper integral and it's this huge mess. How to actually, and you want to use a comparison test. How do you decide what to compare it to? Well, we saw in the trig function case, oftentimes bounding the trig function is useful, but in other cases, you generally bound it by the most dominant term. So especially if you have a ratio of polynomials, you can essentially ignore all the powers, and it's going off to infinity. You can ignore all the powers except the biggest ones, and that will generally be something that's very good to compare it to. And depending on whether you can be sure that it's greater than or equal to or less than or equal to, and what that will tell you, you'll be able to say something. If you can't be sure, then just use a limit comparison test, which is what we ended up doing here. And that can work. We then also spoke about numerical integration, because there are times when we want to do definite integrals, but we can't. We straight up can't. All right. And so we want to learn to approximate definite integrals. So I reviewed, the left-hand rule and the midpoint rule and the right-hand rule from Calc 1. Still expect you to know those, but we introduced some other rules like the trapezoid rule, and we introduced Simpson's rule, which is these two formulas here. So if you know those formulas, you should be able to plug them in and get an approximation for your definite integral. So you can approximate the integral from a to b of f of x dx via this formula. You can also do it via this formula. And we covered that. So again, here, as you'll notice, we did a few examples. We did a couple examples here. Like this was one for the trapezoid rule. As you can see, there really isn't any calculus technically. It's just a matter of algebra. The calculus came in when we were deriving these formulas, but once we have these formulas, it's just a matter of knowing how to dissect your interval and plugging in the right numbers into your function and plugging that into the right approximation formula. So I'll say here's an integral a to b of f of x dx. Approximate this integral using the trapezoid rule with 4 subintervals, or approximate this using Simpson's rule with 4 subintervals, or approximate this using the trapezoid rule with 6 subintervals, or whatever. You just follow these formulas. And we did those for 2 examples. Then we started talking about the next phase of the class, which is focused on sequences and series. And towards the end, we will talk about some of their applications. So, and by the way, from this point on, the material for test 1 is finished, right? So test 1 material is everything back, right? So from there up, that's what you need to know for test 1, right? This is just additional stuff, and I might put in some bonus problems on this. And I don't think I put bonus problems on all the practice exams, but you can expect them on your test. I think one of your practice exams has some bonus problems where I ask you about sequences and series. But if you
will those contribute to our score?
Yes, but they're extra credit. So it's after you finish the test, you'll have an option to, I might throw in some extra problems that if you finish ahead of time, you can try them. And it would contribute to the score. Yeah.
Cool, thank you.
Right. So it's for those who are going at trying to go ahead and get some extra points. Yeah, I'll talk about sequences, which there's not much actually to talk about sequences. I can ask you about whether they converge. And another thing I'm going to ask you about maybe is if they're increasing or decreasing, which we'll actually talk about now. And those two things are relatively simple to do because they just come down to taking limits. Well, for convergence, and I would assume everyone is comfortable with doing that. So sequences, these are just a list of numbers in some definite order to us. So there's a rule or a formula that we're thinking about that creates this list of numbers. And when we have such a list, we call it a sequence. We can name sequences with letters, usually a lowercase letter, and we can use subscripts to track the position of each element. So the elements of a sequence, these are called the terms of the sequence. And so I can talk about a sequence AN, and the terms in this is just A1, A2, A3, A4, A5. And these are just the names I'm giving to each of the numbers in the sequence. And you can have a finite list or an infinite list. The finite list is not going to be our focus. The infinite ones are much more interesting. And the infinite ones are also the ones that have this property or may have this property that we call convergence. And convergence is just us trying to track does the trend of these numbers settle somewhere? Okay, so I can look at the limit as we approach. So if I have a sequence and I can describe it in terms of a formula, I can take the limit of that formula. And if that approaches a real number, that is finite real number, then I say the sequence converges to that number. If it does not, either the limit does not exist or it goes to plus infinity or it goes to minus infinity, I say the sequence diverges. Okay. And whenever you're taking a limit of a sequence, it is always as you go to infinity. It does not make sense to talk about it otherwise, because if you plot the graph of a sequence, they're not like a continuous curve. They're like isolated dots, and you can't actually get arbitrary close to some point. So it actually doesn't make sense to actually talk about, say, the limit as we approach 3 of this sequence. It doesn't make sense to ask that because you can't actually approach 3. There's a gap between 3 and the position 3 and all the other positions. But, this green kind of represents a trend. And sometimes it's like these numbers are kind of settling somewhere. So for example, this sequence, an equals 1 over n, settled at 0. It converged to 0. And we can figure that out just by taking the limit of 1 over n as n goes to infinity is 0. And of course, because we know it's always as n goes to infinity, I don't really have to write it. So you can if you want to, but you don't have to, because that's always going to be the case for sequences. We also looked at a divergent sequence, which was an equals n. So this was just, this was just a list going off like, oh, n equals 1, 2, 3, 4, 5, 6, going off forever. Now this guy diverges, unless you're doing string theory or something, it adds up to, well, no, string theory we'll talk about like the sum of this guy, which is, maybe we'll talk about that later. And this diverges according to the limit. We have something like this. This is actually an important expression, -1 to the n. You're actually going to be seeing that a lot. It's a way to get an alternating sign. So it's +1, -1, +1, -1. So if I want to alternate signs, sometimes what we can do is multiply each term by -1 to the n, and this will get us to alternate the signs, especially if the things had a common sign across the list anyway. And we saw that this one also diverges because the limit doesn't exist. It just bounces up and down between plus or -1. It never settles anywhere. And then we went on to this example, which we didn't actually finish. And we're not going to actually draw a picture of this one because that's going to take forever. But it includes this weird symbol, n factorial. And we discussed that it wasn't about me like and shouting at you for emphasis. It actually means something mathematical. It meant what we call n factorial. So this is an operation that is defined on all non-negative integers. And it's defined as the product of all integers up to n. Unless it's the case where n equals 0, it is defined to be 1, which there are a bunch of reasons why this would make sense. We're not really going to talk about why does it make sense that 0 factorial is 1. We're not going to get into it. But there are a lot of intuitive reasons why we want to make this definition, and is actually consistent with future mathematics when you kind of extend the notion of factorial. So that's kind of where we left off, where I described what a factorial was. And so now we're going to pick up with looking at this sequence and see what it converges to. Now, that brings us to today. I just recopied this here. So now we're going to actually talk about it. So I want to do, well, maybe I should ask, did anyone actually try this and saw what happened or have an answer for like this sequence, n factorial over n to the n? So there are a couple ways to do this. One way is actually very intuitive, and it's actually from something you might have seen in Calc 1. I think I actually put a placeholder here. So in Calc 1, you learned about relative order of terms. So you kind of learned, you know, if we're comparing these different kinds of functions, which ones would dominate if we're going off to infinity, right? So you sort of learned about how to compare logarithms to polynomials to exponentials, etc. And so there was this relationship where it's like, okay, logarithms were one of the functions that were the least dominant, in the sense that they were at the bottom of the list, right? So if I look at the logarithm of the n, right, where n is my variable, this is going to be, I put that symbol here, then that. So what this means is much smaller as n goes off to infinity. Okay. And so something that looks like log of x is going to be much smaller than something like x to the n, for example, x to a number. And so you also know that, so logarithms are less dominant than polynomials, which we know are less dominant than exponentials. So that would actually be much larger than a polynomial as your n is going off to infinity. And this will be, factorial would be the next kind of function up. And then like this exponential with the base also growing as well as the power is going to be the next one up. And this here is for a greater than 1, n greater than 1. Okay. So the idea is the following. As n is going to infinity, guys on the right are much larger. Let me specify here. The log n is much smaller as n goes to infinity, much smaller than n to the a as n goes to infinity. So this just tells you the order of terms. So it means like the log of n is much smaller than a polynomial. Logs are smaller than polynomials. Polynomials are smaller than exponentials. Exponentials are smaller than factorials. Factorials are smaller than, you know, this kind of variable exponential. And that actually helped you in Calc 1 compute a lot of integral, a lot of limits easy. So for example, if someone were to ask you, oh, what is the limit as x approaches infinity of ln of 3x plus 1 divided by x cubed minus 7x plus 12? And you would immediately know that the answer is 0 to that question, because the numerator is a logarithm, the denominator is a polynomial. Polynomials beat logarithms. A polynomial is much larger than a logarithm as the arguments go off to infinity, which means as you're growing off to infinity, the denominator comes so large that the numerator is effectively 0. Might as well not even try. And so you can kind of go along with the idea that, oh, this here, the denominator will overwhelm the numerator, and I know the answer is going to be 0 because the top gets so much smaller than the bottom as x goes to infinity. And you can talk about this being bottom heavy, at least. That's why I told my class to write down, you know, you don't have to show work for something like this, just write bottom heavy. So you just know, I know you know what you're looking at. And the opposite would also be true. So if you have something like x cubed plus 5x divided by ln of, and it doesn't matter how big this is. It could be ln of 1000x, that it won't matter. The ln is going to be much smaller than the polynomial as you go off to infinity. And so this will actually be infinity because now the numerator will overwhelm the denominator. So you have a huge number on the top and a very small number on the bottom. It goes off to infinity. And so this would be like top heavy. So we saw this kind of relationship in Calc 1 when we were looking at these sort of functions. And so in that sense, you can kind of know what's going to happen to this guy if I were to take the limit of an. That's just the limit of n factorial over n to the n. And now because I know that n to the n is much larger than n factorial as n is going off to infinity, what would be the answer here? What would this limit be in light of what I just mentioned?
Is it going to be 0?
It would be 0. Why? Because it's bottom heavy. The n to the n is a much larger function as n goes to infinity than n factorial. So much larger that n factorial you might as well be considered 0. It might as well be nothing, right? Might as well not even try. Someone else coming in here. And so, yeah, so you can kind of know that that's going to be true. There's another way to see this. Some sort of intuition as to why this would be the case. Well, if you look at, say, n factorial, n factorial over n to the n, and you kind of write out what the n factorial is, well, this will just be like n times n minus 1 times n minus 2 times, it's going all the way down to 3 times 2 times 1. While the denominator, it's just n times, right? So this is just n times n times n times n times n times n. And if you were to just, you know, break this fraction up, this this first part, of course, goes to 1. But notice that for every other, once you come down here, and things start getting smaller, these guys are approaching 0, 1 over n approaching 0. So you pretty much get a bunch of numbers multiplying together, but the end point is going towards 0. So it just kills everything. And so you get that this guy will converge to 0, which you can actually write in this way, right? You write the arrow 0. So this kind of gives you an intuition as to why this is the case. Why is n to the n larger than that? And it's like, ultimately, the tail is behaving like 1 over n, which we know goes to 0 like this. So, yeah. And as for the background intuition, yeah, we have this idea of how different kinds of functions, how they grow. So, yeah, so that's sort of what we need to know about convergence of sequences, like how to test if something converges. It just comes down to take limits. And so, yeah, you need to remember everything from limits, because that will come up. So every sort of limit you've kind of done in Calc 1, I would expect you to be able to do now, because, you know, I can give you a sequence looking like anything. You should be able to take the limit of whatever I tell you. There's something that we can talk about, properties of convergence sequences. So there are some properties here. It turns out that convergence sequences obey all the limit properties that you're used to. So, you know, you can factor constants outside these limits. The limit of a sum is the sum of the limits. The limit of a product is the product of the limits. The limit of a division is the division of the limits, provided the bottom one doesn't approach 0. And if you take the limit of a bunch of things where they're raised to a power, then you can just take the limit overall and raise that to a power, and that will also be true. It's very important that you realize that this only works for convergent sequences. So if your sequence diverges, then none of these rules, maybe one or many of these rules, would actually fail. But if you know that your sequence ahead of time converge, then all these rules still apply. You can distribute limits across sums, you can go across products, you can go across divisions, limits can move inside of powers, you can factor out constants, all these nice rules. Limits had very nice rules. It's one of the nicest operations in math. There are a lot of things that don't do this well. You know, like raising something to a power doesn't distribute across sums, but it does across products, right? We saw that, for example. But limits do both. Limits do all these things. And so these properties actually take effect when talking about convergent sequences. So if individually I know my sequences converge, then they will behave like this. Now, yeah, this is just another note that's saying that, oh, I expect you to remember everything about limits from Calc 1, including L'Hopital's rule and all that stuff, but we're not going to go over that. Here's another idea, and I think it's the last important idea for this section. We need to know how to describe whether a sequence is decreasing specifically. Of course, if you do the opposite of this, it means increasing, but we kind of don't care about the increasing as much. It's going to be very important for us to know when a sequence is decreasing. Now, decreasing just means each new term is smaller than the previous term. And so you can actually describe that by saying an plus 1 is less than an, right? And this means it's decreasing. And if you have a formula that you can actually take the derivative of, you can actually use derivatives to describe this as well. So your an equals 1 over n. We saw that that looks like this, right? So n equals 1 over n. Is this decreasing? Well, if you say 1 over an plus 1 equals 1 over n plus 1, and an equals 1 over n, hopefully it's clear, but clearly 1 over n plus 1 would be less than 1 over n. The bigger you make the denominator, the smaller you make the fraction. And so you would say, yes, an is decreasing. Another way you can say an is decreasing is by taking the derivative. If you look at an prime, you get -1 over n squared, which is negative for all n. So we know that when the derivative is negative, it means you're decreasing. And so, for all n greater than or equal to 1 is where we started our sequence. Technically, it's true for all n not equal 0 because you're squaring. Right? But in this way, we can talk about a sequence decreasing. There are some other phrases that you might see, like non-increasing or non-decreasing. And this just means you're talking about less than or equal to is applicable. Decreasing means it's strictly decreasing. But if you want to say that, oh, each term could also be equal to the previous term, then you would say non-increasing. So you're just saying it will never go up, but if it moves, it'll always go down, but it's okay if it doesn't move. So it'll never increase. So I can say non-increasing. And that just means decreasing with the potential of being the same as something previous, but it'll either be the same as something previous or less. And that's basically it. So that's just a concept. If you can see that the n plus first term will always be less than the nth term by some, algebraic means, or you can take a derivative and show that it's always negative, at least always negative after some point, you can conclude that your sequence is decreasing after that point. And that's actually going to be useful for what we want to do. So that was sequences. It's a list of numbers in a definite order. Some sequences do this thing that we call converge, and that just means if we take the limit of the formula that gives the terms, it approaches a real number that's finite. If it goes off to infinity or the limit doesn't exist, then the sequence diverges. Continuous sequences, convergent sequences obey all these rules, so you can do a lot of math with it. Convergent sequence. And it's important to know when a sequence is decreasing. And you can actually do this by either one of these checks. You don't have to do both. You do whichever one's easier. In this example with 1 over n, either one was pretty easy, but it depends on the scenario you're in. Yeah. Any questions on sequences? Okay. So that leads us to section 11.2. So the main thing that we want to deal with here is actually series. So we're going to actually spend a while on series. Like the rest of chapter 11 is talking about series. And we covered enough from sequences to help us in talking about series, because it turns out that sequences are very useful when it comes to talking about series. So now let's actually talk about what a series is. And I did put a definition here. All right. But essentially what you want to think about a series is it's a sum. So series is another way to say that you're summing stuff up. So you actually want to be adding things together, and you can call a sum a series. Now, of course, for us, we're going to extend this notion and talk about infinite sums, adding up an infinite number of things, which might seem a little bit crazy, but you're going to realize that it's not that crazy eventually. And so people usually reserve the word series for infinite series. If you're adding 2 and 3, people usually don't say, oh, I'm calculating the series of 2 plus 3. No one says that. No, you're summing 2 and 3. But series is kind of like generalizing the notion of a sum. And you want to generalize it to adding up an infinite number of terms. So I want to talk about a kind of funny situation or motivation for wanting to know how to do this. But there are, of course, other concrete motivations. And I wanted to talk about one of Zeno's paradoxes. So you might know this guy, Zeno, lived in, 5th century BC. And he was one of those guys, he used to like come up with all these paradoxes. And one of the ones that he came up with was, well, I can tell you both. The actual story was he's making up this story of, I think it was Achilles, maybe. Oh, like Achilles is like racing a tortoise or something like that, you know, and the tortoise has a head start and, you know, they're going to race to some finish line. And he's trying to make the argument that, you know what, I think the tortoise is going to win. And so his argument was the following, right? So if you want to do anything or accomplish anything or cover some distance, you first have to do a part of that thing. Like everything is a process. And so for Achilles to cover the distance between him and the tortoise, he first has to cover half of that distance, right? And then once he gets there, he then has to cover half of that distance. And then once he gets there, he has to cover half of that distance. Before he can close the distance between him and the tortoise, he has to close half the distance between him and the tortoise. And so the idea was, oh, this is a paradox. Will he ever reach the tortoise? No, because he's always trying to get halfway between him and the tortoise. Like, how is he ever going to catch up to it, right? And you can kind of extend this to this other idea of like, how does anything get in motion, right? So if I want to walk a mile, right, first I have to walk half a mile, right? But then after having walked half a mile, I then have to walk a quarter of a mile, right? I have to be able to cover half of the mile. And then half of the mile, I'd be able to walk an eighth of a mile. And so if I want to walk a mile, I can conceive of this mathematically as me kind of doing this infinite sum, right? I have to walk a half unit, then a quarter unit, then an eighth unit, then a 16th of a unit, then a 32nd of a unit. Like I have to cover all these distances to be able to walk that mile. So I can kind of break up a mile into this kind of infinite sum. And now you're trying to argue, well, is that even possible? How does anyone actually walk a mile? How does anyone get anything done when there's like, you can break up a process into this infinite process? And so that was a paradox that, you know, plagued people for a long time, led to all sort of metaphysics about, oh, you know, reality is discrete and blah, blah, blah. And they come up with all these things that kind of explain this paradox. But we are actually going to solve this paradox using math. Yeah. Okay. So can we actually add this up? Does it actually make sense? And would our intuition be correct in guessing that the answer should be 1, right? I take a half plus a quarter plus an eighth plus a 16th. You can conceive of slicing up 1 unit or 1 mile into this. So you can guess maybe that should be like 1, but does that even make sense? What does it mean to like add up an infinite number of terms? This is the idea. And by another token, you might wonder, well, does this make sense to ask in general, adding up an infinite number of things? It seems almost nonsensical, like you'd never get to the answer because you always have an infinite number of things to add up, until you remember that you guys are actually in calculus, which means you did integration, which means you found the area under a curve by adding up an infinite number of areas of rectangles, right? So that's what a Riemann sum was, right? You want to find the area under this curve, and we saw this last class. You dissected the interval into subintervals, you put rectangles on it, and you add up rectangles, the areas of these rectangles to approximate the area under the curve. And the idea was, if you keep doing this infinitely often, you'll fill in all the gaps that you're missing, and you'll be able to get to the area under the curve. And you actually did an infinite Riemann sum, and that was how we defined the definite integral, right? The integral from a to b of f of x dx was actually the sum of an infinite number of rectangles under the curve f of x, an infinite sum of the areas of rectangles. And so this is actually something we should be able to do. Like, we have calculus and we've been doing it, but now we actually want to go back. We actually want to talk about this in general. What if I'm not in the context of an integral, but just for whatever reason, I want to add up an infinite number of things? What is the process for actually doing that? And what does it even mean to do that? What does it all mean, Basil? Right? So in order to make sense of this, we're going to go through, we're going to define our terms. We're going to define the notion of what it means to add something, even an infinite number of things. And that's going to eventually allow us to tackle this problem. And then we're going to go back to the dichotomy paradox, so-called by Zeno. And we're actually going to solve it and see how can we mathematically justify the intuition that we should be able to walk a mile. I've walked a mile before. And actually get the math to agree with us, even though that's probably not the right way to put it. So as I mentioned here, a series is just a sum, but to be constructive in our mathematics, we're going to define it specifically as the sum of the terms of a sequence. So I have a list of numbers, and I just want to add up this list of numbers. So I have a list of numbers in a definite order, right? And then I'm saying, oh, let's add up all these numbers. That is called a series, right? So that's it. List of things, we're adding them all up. So given a sequence AN, we may want to find a corresponding sum, right? So I have A1, A2, A3, A4. I want to talk about what is A1 plus A2 plus A3 plus A4, potentially going on forever. And I can write that down as what's called a series. And this is the notation of that series. So whenever you see this guy, and you've seen this notation before, but just to remind you, this actually means, oh, I'm taking A1 plus A2 plus A3 plus A4 plus, and because there's an infinity up here, it never ends, right? So that tells you never ends. Right? And this tells you the starting point. Okay. Here n is called the index. Right? So if you hear me refer to indices or an index, that's what I'm referring to. It's the guy that keeps track of the position you're at, right? So when the index is 3, this means I'm looking at the third guy in the sum. Okay, but that is what a series is. And I mean, you should know that, although technically I'm never going to ask you that definition. It's something that you should intuitively know. I'm talking about a series. A series is the sum of the terms of a sequence, potentially an infinite sum of terms of sequences. Now, you do also have finite sequence, finite series, too many S words, right? So I could stop it at K and just say, oh, I'm adding up K terms, adding up A1, A2, A3, all the way up to AK. That's also doable, but we're not really going to worry about that because we know how to do that, right? We know how to add up a finite number of things. If I give you a list of things, it might take you a while to do it, but you know how to do it, right? What is confusing potentially is doing this for an infinite number of terms. How do I even finish to get an answer? Okay. So I guess here I did talk about that. So maybe I should talk about that here. This is plural of index. Right. So that's this guy. The n is called the index. I did make some space to talk about that. All right. So now this leads us to the question of how do we actually make sense of an, the sum of an, right? And adding up an infinite number of terms, how does something like this even make sense? And so the idea we're going to develop, because we want it to be consistent with mathematics, right? So I want to capture the notion of addition. I don't want addition in the infinite case to be something completely radically different from in the finite case, right? The notion that I come up with has to work in all cases. Math, we want it to be consistent. So we're actually going to use a finite situation. Say I want to add up the numbers 1 through 5. How would I actually go about doing that? Okay. And we're actually going to use a very basic principle here. we can do something like, well, I mean, you can think about it. Like if you gave someone, maybe a child who recently learned how to count, recently learned how to add stuff up, and you gave him 5 things to add up, right? You know, it's like, okay, he knows, okay, if I have 2 toy trucks and you give me 3 toy trucks, I have 5 toy trucks. He knows that, right? But what if you gave him 5 groups of trucks, right? Like, okay, you have 2 toy trucks in this pile, 3 toy trucks in this pile, 4 toy trucks in this pile, 5 toy trucks. Like, how would that person go about adding that stuff, that up, do you think? Like, what would they do? What do you think? Like, how would you approach that problem?
Probably just count how many are in the pile and then add up the number of piles you have.
What if they have different numbers of things in each pile? Right, like you give them a list of numbers to add up, right? Oh, you know how to add 2 plus 3? Okay, what is 1 plus 2 plus 3 plus 4 plus 5? Like, how do you think someone would go about that problem?
Maybe you could look at it in terms of rates of change. Like how is it
Oh,
changing?
that's way
as
too
it goes?
complicated. Like your 5-year-old isn't going to come up with the rates of change. Like, what would they do?
Just go
Count them
chronological order.
individually.
Oh, I had a couple. Yeah, what is the idea?
Count them individually.
What does that mean? Like, describe to me the process that you do.
You have 1, 2, 3, 4, 5. Just count how many numbers are there. So you have 1, 2, 3, 4, 5 numbers in that whole thing.
Yeah, but that's not what I'm asking. I'm adding these guys. 1 plus 2 plus 3 plus 4 plus 5. Right? So the answer should be 15 at the end, but how would someone get there? Like, you gave someone 5 things to add up. Like, how are they going to do it? Well, yeah, I know I want to add them, but how? You guys don't have like little brothers and sisters, or you guys so old you don't remember being young? You guys don't remember being young and learning to add for the first time? They would actually do it like sequentially, cumulatively. So they know how to add 2 things. They'll just add 2 at a time. So what they'll do is they'll add the 1 and the 2, and then they'll add the 3, then they'll add the 4, then they'll add the 5. They'll actually kind of group things in their mind and just keep adding on the extra as they go on, right? So I know the 1 plus the 2, that's going to be 3. Then they add the 3, that makes 6. Then they add the 4, that makes 10. Then they add the 5, that makes 15. And so they would eventually get to the answer of 15 because they don't have the notion of adding up 5 whole things. They just know the notion of adding up 2 things. Well, if you add 2 things at a time, you can eventually get to the process. So it turns out that this works with finite addition. And this notion actually will work nicely with infinite addition as well. So the idea is you would actually add it up in a cumulative way, right? So, and I typed that out, you add the 1 and 2 and then blah, 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 right? So let's actually make that into something a little bit more specific. It turns out that when you're doing this cumulative sum, right? You're adding up things and then you have the sum so far and then you add something else and you update the answer and you add something else, you update the answer. It turns out that you can actually create a sequence of these answers, right? Now, these things, when you're just adding up a part of the answer and then adding on the other part, these guys are called partial sums. So these here are the sum so far can be thought of as a partial sum, right? So if I have like A1 plus A2 plus A3 plus A4 plus A5, and that's like my 1 plus 2 plus 3 plus 4 plus 5. Notice that this was just A1, this would be A1 plus A2, this would be A1 plus A2 plus A3, and so on, right? These things are called partial sums, and it's a cumulative way of adding. You just add up so far, then add one more number, then add another number, then add another number. And you can actually, you just do this until you get to the end. And what you'll realize is that eventually, if you follow this list of numbers, it will end at the answer. This sequence will converge to the answer. And I know this is a finite sequence, but if you kind of just think of convergence, you just stop it as whatever the answer is, then you'll see that this sequence converges to the answer. So you can actually do this with a finite list of things. You'll always get the right answer by doing this process. Just add up partial sums, add cumulatively, add to one thing at a time to your group. And eventually, this will give us the answer. So you can actually create a sequence that tracks the addition up until some point. Eventually, if it's finite, this process will end. It will end on the answer. But the idea is, if it's infinite, it never actually ends. However, if I could describe this as a sequence, which it is a sequence, it's not just a random list of numbers. It is a list of numbers where I know a definite process that's going on in the background. I can then talk about convergence in the general case, in the infinite case. And so you can generate with any sum a sequence of partial sums, and we can talk about that sequence as being Sn, where Sn, the nth term, is just defined to be the sum of the first n terms of our series. And with that definition, we can actually talk about a series adding up to something. What does it mean when I say this infinite sum equals something? Well, what it means is that I can describe this infinite sum as a sequence of this type, and then I can check what it converges to, and that convergence will be the answer. This will work in the finite case. It will also work. We'd also want it to work in the infinite case. Now, we don't even know if this is going to be possible, but it turns out it is, and that is our definition. What does it mean to add up an infinite number of terms? And we use the same language because in the background, we're thinking of the limit of a sequence. We say a series converges to a real number S, and we can even write that it's equal to S if in the event that our Sn converges to S, and Sn is the sequence of partial sums. So if we can cumulatively add something and get somewhere, we'll consider that to be the answer. Otherwise, if your S goes off to infinity, or it bounces up and down and it doesn't really get to an answer, we say that the series diverges. Diverges. Series is actually singular here. And so that is what we will take as our definition for what addition means. Addition means you look at the convergence of sequence of partial sums. Whatever that converges to, that is the answer of your addition. And this works across the board. This is the notion of what addition is, right? So if you don't have to get to the end, technically speaking, to actually know what something is going to add up to. Like you can know what the process is and you'll know where it ends up. And in the finite case, it's kind of easier to know where it will end up. In the infinite case, we can use limits to know where it ends up. And so that is going to be our definition for adding up an infinite number of terms. And we'll see that this will actually help us get to some very interesting ideas and some interesting math that actually works out in the real world. But for now, we're going to take a quick 5-minute break, and then we'll talk a little bit more about actually putting this definition to use, to actually getting to the bottom of things, some answers. So I'll see you guys in a little bit. And we're back. Okay. So quick recap, just again, series is the sum of terms of a sequence. Series can be infinite or finite. We really care about the infinite case. We're not really going to talk about the finite case. And we want to talk about what notion we're going to use to determine if this adds up to something meaningful or not. We have the intuition that it should, based on like the dichotomy paradox, and we've been doing things like finding Riemann sums. But we actually want to kind of generalize this notion. And so we've spoken about the notion of a partial sum, right? So there's an infinite number of terms to do something, but we can talk about adding up the first 2 terms, the first 3 terms, the first 4 terms, the first 5 terms, the first 6 terms, the first n terms at any given stage, and kind of keep pushing n further and further. This is called the sequence of partial sums. And that's defined to be the generic variable used there is s sub n for a sequence of partial sums. And that just adds up the first n terms of any series. And the idea is, if you can describe what the sum of the first n terms look like, and you take n going to infinity, this essentially gives you what sum of all terms would look like. So that's the idea. And this is a notion of addition that we really like because it falls in line with what we understand intuitively works with finite addition. So finite addition is technically defined for only adding 2 things. But the idea is, if you have more than 2 things, you just add 2 things at a time, and you keep making one of those things the sum that you have so far, and then adding the other thing to it. And that thing, the sum that you have so far, we give it the name, the sequence, a partial sum. And if we think of all of these guys as a list of numbers that we can cumulatively build up, we call it a sequence of partial sums. So our series will converge if there is a sequence of partial sum that we can describe the terms with, and that converges. And so this is where the convergence of a sequence actually comes in handy. It's actually a very important thing to know. So this is kind of an important thing to know. This might come up. What a sequence of partial sums is. It just really means the sum of the first n terms. Okay, so let's actually apply this to the dichotomy paradox, right? And I mean, it's been like a millennia and a half since this was posed, but you know, better late than never. Let's solve this thing. Can we actually walk a mile? Let's see. So let's actually do the process that we kind of described that that we want to do. Let's actually construct the sequence of partial sums. Okay, so we have S1. That is just the sum of the first term. So we know that's a half. Okay, so far so good. S2 would be the sum of the first 2 terms. So that would be a half plus a quarter. Okay, cool. What's that? Can multiply a half by 2 over 2. And so I get 2 over 4, and then add that to 1 over 4, I get 3 over 4. Okay, so far so good. What would S3 be? That's the sum of the first 3 terms. So it's a quarter plus a fourth plus an eighth. All right. So I know that's really 3/4 plus an eighth, right? So it's the sum that I have so far. Now I'm adding 1/8. So I can multiply 3 over 4 by 2 over 2. That's 6 over 8 plus 1. That gives me 7 over 8. And I can continue. S4, sum of the first 4 terms. Well, that's going to be the sum so far, plus me adding this 1/16. And 7 over 8 is really 14 over 16. And then I add 1, 15 over 16. And so we can actually continue this process. Of course, I do not have forever to spend doing this. So now I'm going to try to figure out, is there a general way to define to describe this process. Any ideas as to what this would actually look like? Like if I look at these numbers, this pattern, right? Like a half, then 3/4, then 7/8, then 15/16. The next one, by the way, is going to be like 31/32. Any pattern that you see here?
It looks
Getting
like,
close.
Was that Danielle?
Yeah, I was gonna say it's getting closer to 1.
Sure, but I actually want to describe each term with a formula. You see Sn, I want to get a formula here. Can you tell me a formula that it's a half when n equals 1, it's 3/4 when n equals 2, it's 7/8 when n equals 3, it's 15/16 when n equals 4? Is there a pattern that you can look at or see that will actually give you such a list?
it looks like 2 to the n minus 1 over 2 to the n.
Yeah, 2 to the n minus 1 over 2 to the n. So one pattern you can see is that the numerator is always 1 less than the denominator. So that's cool. So if you can find a pattern for the denominator, the numerator is just going to be that minus 1. So that's awesome. And so what is the pattern for the denominator? Well, 2, then 4, then 8, then 16. This is just successive multiplications of 2's, right? 1 is 2 squared, right? So this, you would realize this was like 2 to the 1 minus 1 over 2 to the 1. This is like 2 to the 2 minus 1 over 2 to the 2. Here, the denominator was 2 cubed. Here, the denominator was 2 to the 4th. And then on top, it's just 1 less than that. So you can actually know what the pattern is going to be for the other one. So the next one would be 2 to the 5th minus 1 over 2 to the 5th. So this would have been 31/32. And then the next one would have been 2 to the 6th minus 1 over 2 to the 6th. So this actually describes the pattern in general. That gives me my sequence of partial sums. Now, I can write this as like 1 minus 1 over 2 to the n. And so now, by our definition, if I were to add a half plus a quarter plus an eighth plus a 16 plus ... plus at the end. This is like me taking the sum and I'm adding like, well, this is like 1 over 2 to the n, right? N goes from 1 to infinity, right? So it's 1 over 2 to the 1, then 1 over 2 to the 2, then 1 over 2 to the 3, then 1 over 2 to the 4, and that's continuing. And by our definition, this is equal to, well, the limit as n approaches infinity, well, it's always going to be infinity, of Sn, right? So this is where the definition comes in. But what does that mean? Well, this is just the limit of 1 minus 1 over 2 to the n. What's that?
One minus 0.
Right. So 2 to the n, the denominator that approaches 1 over 2 to the n approaches 0 because 2 to the n is going to approach infinity. And so it's 1 minus 0. Turns out this adds up to 1. So we can walk a mile. So reality is actually not messing with us. This notion of being able to dissect something into an infinite number of parts and add them up to get the whole, actually, it works out with our intuition and it works out with mathematically what we think addition should work like. So this makes a lot of sense, makes us very confident. This is the definition we're running with So it turns out we can add up an infinite number of things, provided that we can actually do this. We can find a sequence of partial sums to describe the thing. And if that sequence converges, then our sum converges. We'll consider that to be the answer. If I add up all these terms, this is what I'm going to get. And in this case, if I add up all the terms that look like this, I get 1. So yeah, that works out to a mile. So yes, we can actually get someone. I guess Achilles can catch up with that tortoise after all. Okay. All right, cool. So let's actually talk about a couple more definitions. So I want to talk about the notion of a series. So we all understand what it means for a series to converge, right? So a series converges if its sequence of partial sums converge, and then we consider the answer to the series, what it adds up to be what the limit of partial sums converges to. Now, there's a different thing we can do. So if I give you a series, so I'm giving you a series, sum of an. Here's something that I could do with that. I could just put absolute values around each term for whatever reason. We're going to talk about why this might be important later. So it's like I'm adding up all the terms now, except just with absolute values around them. Right? Now, so given a series an, if I look at this series with absolute values around it, if that series converges, then we say that the series an converges absolutely. And this is the term that I want to define here. So this is the definition that I want to define. Okay. So I can have a bunch of terms that I'm adding up. If I go in and I put absolute values around all the terms and it still converges, it still adds up to some number, I say the original series converges absolutely, meaning it converges with absolute values around the terms, right? Okay. Now, it's possible for this to not happen. It's possible that the original series will converge, but if I put absolute values around everybody, it doesn't converge anymore, right? So you can think of this as like a list. I'm summing up a list of terms, but some of them are negative. So you realize that they're decreasing the sum, right? So I add something and then I subtract something and then I add something and subtract something, I add something, and then this actually adds up to a number. But if I don't subtract anything, I just add everybody in magnitude, it gets too big and it goes off to infinity, for example, right? So it can happen, you know, especially when I have a mixture of signs, like some things are positive and some things are negative, and I'm adding them together. Sometimes if you took away all the negatives and made them positive, it will diverge. Sometimes it converges as well. So if you take the absolute values of everybody and it still converges, we say it converges absolutely. If it converges, but when I put absolute values around it, it doesn't converge anymore because now everything gets too big and it adds up to something too large, I say it converges conditionally. I say it converges conditionally, right? So converges absolutely means it converges with absolute values around all the terms. If it converges originally, if I just leave everything alone and it converges, but when I put absolute values around everybody, it doesn't converge anymore, I say it converges conditionally. It converges on the condition I just leave things as they are. Don't touch anything. Then it's going to converge, right? But if I can go in and put in absolute values around everybody and it doesn't change the fact, it might converge to something different than it did originally, but it still converges. There's a finite number that all these things add up to. I say it converges absolutely. Okay. Now, of course, it's important for you to know, of course, that if something doesn't converge in either sense, then it diverges, right? So there are two kinds of convergence when it comes to series, right? So when it came to sequences, just a list of numbers, and we're talking about them converge, there was only one kind of convergence. Just take a limit, see what the answer is. When it comes to series, there are two kinds of convergences that we are going to care about. There's absolute convergence or conditional convergence. So absolute convergence means I look at this list, this sum, I put absolute values around them, and it converges. Then I say it converges absolutely. If I look at this sum and it converges, but then I put absolute values around it, and then now it goes off to infinity or it diverges, then I say, oh, it's conditionally convergent. If I look at a sum, it doesn't converge, I put absolute values around it, it doesn't converge, like nothing is going to make this converge, then it diverges. There's no way to stop it. It's just not going to add up in anything meaningful. And at first you might wonder, well, why is it important to refine convergence this way? Why do we want these two different kinds of convergence? Because it turns out when you're doing an infinite number of things, like usually when you throw infinity into the mix, a lot of things get messed up in very tricky ways or very unusual ways. So this is not the issue here arises because we're doing an infinite sum. It wouldn't be a problem with a finite sum, but there's something called the rearrangement theorem, which is a very interesting thing to think about. So go back to our little history lesson. Riemann, remember guy Riemann, the guy who invented Riemann sums? So, you know, early 1900s, he wrote his PhD thesis, and included in that thesis was Riemann sums, where he showed an alternative way of computing integrals, right? Which we call the Riemann integral. There are many ways to actually compute integrals, but the version you learned in Calculus 1 was the version invented by this mathematician named Riemann. And he developed that new method within his PhD thesis. Now, in that thesis, which was, you know, roughly 100 pages long, like one of the pages, there was something in there called the rearrangement theorem. And basically the theorem said the following, right? Because he was dealing with sums, he had to learn how to compute Riemann sums. I don't think he called that himself. That would be very... He was learning how to compute Riemann sums. In his mind, the sums he was caring about was adding up areas of rectangles. But of course, you need something to be mathematically consistent. He had to extend this notion to be able to compute sums of any sort of things. The numbers could have any interpretation. What he realized was the following. If you take a conditionally convergent series, and R is any real number you want, pick your favorite real number, pi, E, 17, 13.9, pick any real number you want and take a conditionally convergent series. That means it converges, but if I throw absolute values around it, it diverges. Here's the thing that he discovered. In this case, it is possible for you to rearrange the terms so that it will add up to that real number that you picked. So he can have a series and it adds up to 5, but it's conditionally convergent. It turns out it's possible for you to rearrange the infinite number of terms so that it adds up to pi, or it will add up to E, or it will add up to pi squared over 6, or it will add up to 17, or it will add up to 13.9. You would be able to rearrange these terms so that when you add them all up, according to our definition, you can get it to be anything. On top of that, you can rearrange the terms in such a way that suddenly it diverges. So I had a series that I know converges to 5, but it doesn't converge absolutely. It turns out I could rearrange the terms so that it adds up to anything I want, and I can rearrange the terms so that now it adds up to infinity. Now it adds up to negative infinity. Now it adds up to anything, right? You can literally rearrange the terms and change the answer. Now, when it comes to finite sums, we know this is not the case. We have a commutative, addition is commutative, we say. It means it doesn't matter the order you add them in. 2 plus 3 is the same as 3 plus 2. It turns out This is not true when you're adding up an infinite number of things, except in the case of absolute convergence. If your series converges absolutely, then all rearrangements will converge to the same number. So if you have a series originally and it's absolutely convergent and it converges to 5, no matter how you rearrange the terms, you will always get 5. That is 5, right? And there's no rearrangement can change that. So it turns out there's a distinction between the way things can converge, and it can have like a lot of consequences that, especially in math, we'd want to look out for. So in other words, community of addition only holds for sums that converge absolutely, right? It does not hold for conditionally convergent series. So if your series is conditionally convergent, you can rearrange the terms to converge to whatever you want, including if you want it to converge to infinity or diverge, as we would call it. So that is actually very important. Here's one reason why it's going to be important, because we're in calculus, right? So which means we don't really care about, you know, the arithmetic behind it. We're going to want to be able to do derivatives and take integrals and all of that. And so the question comes out, it comes down to, what if I wanted to do something like integrate the terms of a sequence, right? Like what if I wanted to say, I want to find the antiderivative of this guy, you know, like n goes from 1 to infinity of an with respect to n. Well, that would mean I would integrate, you know, a1 plus a2 plus a3. And remember, these are functions of n, right? They have n's in them, right? A1 of n plus a2 of n plus a3 of n plus da 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 dn, right? Now, we know how integrals work and how we would like them to work. We'd want to be able to split our integral across the sum, right? We saw this when calculating integrals. Sometimes you have to split up an integral to be able to compute it. You know, you want to be able to do integration by parts on this part and do integration by substitution on this part. Like splitting up an integral is a very fundamental thing that we'd want to be able to do. So this, you'd want to be able to say that I can integrate a1, and then I can integrate a2, and then I can integrate, you know, a k, and I'm putting dx out of habit, but the actual variable doesn't matter. I can call it x or I can call it n, doesn't matter. Like I'd want to be able to do that, right? Now it turns out is, so in other words, this is what we'd like. I would like to be able to take a sum of each thing integrated individually. So it turns out this is not always true. You cannot always make that assumption. And that means a lot, right? So it, and we'll actually be doing this, by the way. So this isn't just something like I'm just making up a problem out of nowhere. No, there's going to come a point where we are going to want to be able to integrate series. And we are going to want to be able to do something like switch the order of the summation and the integral sign, right? So the integral of a sum is something that looks like this, where the sum of the integrals is something that looks like this. And it turns out the only way for those two things to be the same is if my original sum converged absolutely. If they converge conditionally, then my integral has no meaning, because I can just integrate in different pieces in different orders, and now I get a different answer. My integral wouldn't have an answer. right? So it turns out that you can't differentiate a series and you can't integrate a series and you can't take limits of a series if the series is conditionally convergent. Because what that means is you can rearrange things and get a different answer every time. You'll never be able to pinpoint, you'll never be able to say, oh, this is 5. You can't say that because, oh no, it depends on what order you're doing it in, right? So that's the rearrangement theorem that tells us that. Order doesn't matter when you're adding stuff up, except if the thing is infinite and it's conditionally convergent, right? If things are absolutely convergent though, then the same intuition that we have from finite sums carries over to infinite sums. We can do it in any order we want, right? 2 plus 3 is the same as 3 plus 2. And we need absolute convergence to get that to work out. So yeah, there are different notions of convergence, but it's actually important for us to pay attention to these. And there's going to come a point where I'm going to ask you to actually distinguish between these two. Like, you know, something's convergent, tell me, is it absolutely convergent or just conditionally convergent? So yeah, that's an important thing to know, right? And so when we're going to want to do calculus, we're going to need to know, or when we want to do calculus with series, we will need to know that these series are absolutely convergent. Otherwise, calculus will not work. And so that's actually very important. Now, like with sequences, we have some nice algebraic properties of series, but you'll notice that this list is much shorter. And, you know, we had properties of sequences earlier. We're at a bunch of things. Oh, all of these things work out. With convergent series, series are a lot more fickle. We know these two things when it comes to like the arithmetic. These two things are true. The other things will not be true. And so, for example, for one, if I wanted to take a sum of a constant times an, this just means I'm adding up c times a1 plus c times a2 plus c times a3. And then I would be able to factor this out. And so this is just going to be c times the sum of an. So I can factor things out of series, and this will work. This will work for conditionally convergent or absolutely convergent series. Because if this changes answer, then this corresponding answer will also correspond to C. Right, so that's true, that works. Similarly, if I want to take, you know, if I have two sequences and I want to add or subtract them, then this just means I'm taking A1 plus or minus B1 plus A2 plus or minus B2 plus A3 plus or minus B3 plus dot, dot, dot. But I can rearrange them so that I'm adding all the A's and then add all the B's. Now, of course, if the rearrangement changes the answer, this corresponding answer will also change. So this actually applies to any series, but it says that I can add up all the guys from the first sequence and then add up all the guys from the second sequence. And that will actually work out. So that is true. Now, the other things aren't true. So series do not distribute across products, for example. So put a warning here, because that is actually a very common mistake that students make, thinking that a series will distribute across a product. It does not, right? In fact, one will always be less than or equal to the other. So it turns out that this one, the AN BN, is always going to be less than or equal to the AN times the BN. How do we know? Well, for this one, all the terms looks like AN times BN. So the first term is A1, B1. And the second term is A2B2. And the third term is A3B3, etc. Now, what about this one? Well, this is saying I'm taking the sum of the ANs, and then I'm adding and I'm multiplying that by the sum of the BNs. So now I have to like multiply out, like I have to FOIL stuff. So I'm going to be like A1B1, A1B2, A1B3. That's going on forever, plus A2B1, plus A2B2, plus A2B3, plus da da da, plus A3B1, plus A3B2, plus A3B3, plus da 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 da, plus da 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 da. Right? There's so many more. And it's like right here, that was from the original term. And this was from the same as the left. And this is the same on the left. Right? So you can see the right side in general will be adding many more things than the left side. And so the right side is actually going to be bigger. So you can't take the sum of a product and think that it's the same as the product of the sums. So all those nice properties about distributing across sums, it doesn't work for series, right? So the only thing arithmetically or algebraically you can be sure will work is these two things. You can factor constants out and they will distribute across sums or differences. But it doesn't distribute across divisions. It doesn't distribute across multiplication. It doesn't distribute within powers. You can't move a summation inside and outside of a power and expect everything to be the same. It's not going to be the same. These two things is what will work. Now, there is something that I want to talk about, a special kind of series. So we saw earlier, and we're going to actually deal with this a little bit more, of course, but we saw earlier that when I wanted to talk about a series adding up to something and I want to figure out what it converges to, we had to develop this sequence of partial sums. I had to add it up in pieces, and then I had to figure out some sort of formula that ties everything together. Then I had to take the limit of that formula, which for this, it wasn't so bad. But in general, it can be a nightmare to actually do this. Like not everything follows this nice little pattern. Oh, a half plus a quarter plus an eighth, where it was easy for, oh, this is the pattern, right? Things can be very, very messy, where a process like this becomes very difficult or impossible to actually do. And so there are a lot of sums that we actually don't know how to add up, but there are a lot of ones that we do. And those can be very useful. Now, there is a kind of summation called a telescoping series, which I think is in the last section of 11.2, if I'm not mistaken. And this is a series that we can actually compute it by relatively simple means. And that's because the partial sums, the sequence of partial sums is such that most of the terms will cancel each other out. And then we'd be left over with something much more manageable to deal with. And this is called a telescoping series whenever that happens. Actually, I'm not sure why it's called telescoping series. I don't know the etymology of this, but this is a kind of series. And so it's the kind of series where, like I said, when you start looking at the partial sums, it turns out that some things cancel each other out, and it makes it a lot easier for you to add them together. Okay, so recall, we say this guy equals S if Sn approaches S where Sn is just the sum of the first n terms. Okay, so that is what it means to add something up. And well, let me use a different letter here because I want to tell about something. So use Sk is just the sum of the first k terms. So we can say that this guy we can think of it as just adding up a finite number of terms, just say something like the first k terms, and then taking the limit as k approaches infinity, right? And that would be the same thing. And so once you understand that idea, it turns out that if you can actually get this to work out very easily, which in the case of telescoping sums you can, then you can actually use that to your advantage. So for a telescoping sum, this is what you can realize will happen. If I look at the sum of the first k terms of this guy, okay, here's what you notice can happen. Notice that this is going to be the sum of this. Now, this here, okay, that is something that we can do partial fractions on. What would the parts be? Of course, it's going to be n and n plus 1, right? What is on the numerator of n? So review for partial fractions. Want to do partial fractions on this? That's definitely the 1 over n squared plus n is a rational function with the denominator factors. The numerator is smaller. Let's factor the denominator, break it up. What is the coefficients here? What are the coefficients?
One and -1.
Right, 1 here, because you can just do the cover up method. You cover up the n, plug in 0, you get 1. And then -1, because if you cover this up and plug in -1, you get -1. So that's what you get. And now what is that? Like if you add up the first k things of that form, what are you going to get? Well, if I plug in n equals 1, that's going to be 1 minus a half. If I plug in n equals 2, it's going to be a half minus a third. If I plug in n equals 3, it's going to be a third minus a fourth. Plug in n equals 4, it's going to be a fourth minus a fifth. Right? Plus dot, dot, dot. So this was, this is n equals 1, this is n equals 2, this is n equals 3, this is n equals 4. Let's look at what the last few terms look like. Dot, dot, dot. So let's suppose we're almost at k. Let's say we're at 2 away from k. N equals k minus 2. Then you plug that in, get 1 over k minus 2 minus 1 over k minus 1. Plus when n equals k minus 1, plus when n equals k. This is n equals k minus 1, here n equals k. Okay, so that's what this entire sum would look like. Now, do you notice anything? What do you notice here? Notice anything potentially convenient? Anything at all? Can you say about the sum? No, no one sees any pattern. Here's one. Minus half plus a half. That cancels. You have minus a third plus a third. Minus a fourth plus a fourth. Minus a fifth. That's going to cancel with the other guy here. Right? Because that would start when n equals 5. When you plug in n equals 5, the 1 over n will become 1 over 5. So that's going to cancel it there. You go down to the last few terms. You notice that this will cancel that. This will cancel that. And this is going to cancel with the guy that was ending here, because the last one was when n equals k minus 3. If you plug in k minus 3 into this part, you'd end up with k minus 2 in the denominator. And so the term before that would cancel out that guy. So now when it's all said and done, you realize that almost all the terms cancel out. You get something a lot smaller. In fact, this would be a minus. You get 1 minus 1 over k plus 1. Okay. Now, this sort of thing happens to telescoping sums, right? We call a sum telescoping when this sort of thing happens. You write down the sequence of partial sums, and almost everyone cancels out, and it contracts to something very small. So as you're adding things up, a bunch of things are dying at the same time. And so you're ending up not adding up much, to say the least. And so this is what the partial sums would look like. Now, if we go by our definition, we just want to take the limit as our index goes to infinity. And so what we can do now is we can say, oh, let k go to infinity of this. And you realize that in this case, the answer is again 1. Okay. So this one also adds up to 1, this sum right here. It's very interesting. You add a bunch of numbers that look like that. So this is like, you know, if you plug in n equals 1, that's a half. plug in n equals 2, that'll be a fifth. Plugging in n equals 3, that'll be a 12th. Right? So you can add up a bunch of numbers according to that pattern, and you can know what they'll add up to. They'll actually add up to 1. If you had an infinite number of time, you can sit around and add up all these numbers, you would add things up to 1 eventually at the end of infinity. And so this is a thing that can happen. It's called a telescoping sum. It means you can do something to figure out that you can conceive of the partial sums as some sort of expression where most of the intermediate terms cancel out. Right? And you just saw one of the most common ways to actually get this to work is using partial fractions, something that hopefully we know very well already, or will know by tomorrow very well. So there's that. So that's an interesting example of a kind of series where we don't need to play this game. We can play another game where it's much easier to actually see how things will work out. You can see it right there. Things are just canceling out, and you're like, oh, we're actually not adding up that much, right? But yeah, like at the end of the day, in this example, like the only thing you add is the first term and the last term. And with that said, we're going to take a break here. So stretch your legs, get a drink of water, and we will continue. All right, and we're back. So talking about series, which is just a fancy name for sum, adding things up together. We really care about adding up an infinite number of things together, which we just saw the example from telescoping series about how we can add up certain series that follow a pattern like this, where all the partial sums have all of the intermediate, most of the intermediate terms canceling each other out. Sometimes there's a nice pattern where we can actually get a formula for the sequence of partial sums, and that can tell us what the series will add up to. But there is a very important comment. Just as with improper integrals, there are times when we won't know for sure what a series adds up to, but we can know whether or not it adds up to something. So like when we had when we learned about the comparison theorems for improper integrals, we saw the situation where, oh, knowing what happens to one improper integral can tell me about what would happen to this other improper integral. And even though I don't know exactly what it works out to, I know that it will converge to something. It turns out that you can do the same thing for series, because there are going to be a lot of times where we can't actually do something like this with the telescoping series, or something like that with this series. And even if we could, sometimes it's going to just be very annoying to actually deal with them. So we're going to talk about some ways in which we can tell when a series will converge or not, without necessarily knowing about the answer. So it turns out that there are many kind of tests that we can do to test series. These guys are usually called convergence tests, or tests for convergence of series, where you can actually use some sort of mechanism to check, does this infinite series add up to something meaningful or does it not, right? And without us knowing necessarily what it might add up to. So I'm going to tell you about 10 tests, and most of them don't tell you what the series add up to. There's probably, I know the one does, but I think there's only one that does so far. So, and I guess telescoping, if you notice a series is telescoping, that would also tell you what the answer is. But that's where we're kind of going here. So sometimes we actually don't know what a series will add up to, and it's very difficult to actually calculate it and find out. But we want to know that it adds up to something. And like we were talking about yesterday, what it turns out, and we'll actually discuss this more in detail with series than we did with integrals or improper integrals. It will turn out that if we know that a series converges, there are ways that we can approximate what its answer is. And we can approximate it to within any degree of accuracy you want. So not knowing exactly what the series adds up to isn't really an issue, generally speaking, because we'll have a lot of other machinery that allows us to approximate this thing. And like I said, a lot of times we can't use the real answer anyway if we know the answer. Like, I know something adds up to pi, like there's no way I'm going to get that in reality. The best I'm going to get is pi up to a certain number of digits, and I can make it so that I can get up to that certain number of digits. I can get to within any degree of accuracy I want. I'll just never get the full picture. And that's okay in general. So there are times when we don't know how to add up series. We don't know what the answer will be. But if we know that they do have an answer, then we'll be able to do something on top of that to kind of approximate the answer. And we'll be able to approximate that answer as good as we need it to be, essentially. We don't actually need to get it perfect. We just need to get it as perfect as the application we want it to use it for needs it to be. And so this is going to lead us into the notion of series convergence tests. And like I said, there are 10 of them, and I actually put them all in a table for you. And so what we're going to do is we're going to spend some time going through all these tests. We're going to teach how to use them. So in terms of, I don't know what I want to say logistically, I don't know. Or in terms of the feel, this is going to kind of be like me teaching you a bunch of integration techniques, and then you really needed to figure out when a certain technique applies to a particular integral. This is going to have that same sort of feel. So it must be the case that I should be able to give you a bunch of series, and even if you can't figure out what the answers are, you should be able to tell me whether or not they converge. You can say this series converges, it will add up to something meaningful. Moreover, you should be able to tell me that this series converges absolutely. So we can do calculus with it, we can rearrange terms, everything is fine. And this series converges conditionally, which means we can't do calculus with it, everything is not fine. We have an answer, and it's only because we are looking at things in a particular order. So you should be able to tell me these things, and you should be able to use one of these tests to be able to tell me these things. And so we're going to spend some time going over these tests. And so sections from sections 11.2 all the way to 11.6 is really going through a bunch of these tests and learning how to use them with series and learning when to use them. And as you can see, there's even a column in this table, when to use. So that will be something that is very going to be very useful. So there is, so that's the next phase. And even though there is a slightly different order here, generally I'm going to be covering these tests in this order, except for the first one. So I actually want to do the kth term test first. So I actually want to do this one first. And another name for the kth term test is the divergence test. Or test for divergence. Which is probably what I want you to remember it as, actually. So the kth term test is what it's called, but the divergence test for divergence is probably what I want you to remember it as. And it might be referred to like that in your textbook. So let's jump in. So we're going to talk about the test for divergence, aka the divergence test, aka the nth term test, aka the kth term test, aka the limit divergence test, etc. I would rather you know it by test for divergence, because that actually tells you very importantly what this test actually does. The test tells you about divergence. That's exactly what it does. This is one of those kind of reverse tests. So it won't tell you when something converges, but it will tell you when it diverges. So it will tell you when you don't have a particular answer that a series will come up, add up to. So here's what the test for divergence says. Suppose you have an infinite series, AN, right? If the limit of the sequence of terms is not equal to 0, then the series diverges. And that's it, right? And, you know, I will make a note of this, as its name suggests. This test tells us when a series diverges, it cannot tell us about convergence. Okay. But just as with integrals, I am going to give you like a strategy for approaching series. And this guy is going to be like one step away from checking the basic rule kind of thing. It's going to be one of the first things you look for, because of all the series tests, it's going to be the easiest one to actually check whether or not it will work or not and give you some information. So it's going to be one of the easiest tests to apply. So I'd want to get that out of the way first. And it's kind of always going to be one of the first things you want to do. So I'm just going to jump into some examples. So that test, what is in the box, is pretty much all you need to know for the test. Right? If the limit is not equal to 0, then the test will diverge. Then the series will diverge. Okay, so let's actually jump into that. So example 1, I have around 4 parts here, I think. Yeah, around 4 parts. And we are going to talk about testing whether or not these guys converge or diverge. So what about this one here? So we have, for example, note here, your an is equal to n to the n over n factorial, right? So what you can say here for this one is you can just go, all right, note the limit of an. Well, that's just the limit of n to the n over n factorial. Okay, and what is that? We did actually cover this today, or cover enough for you to figure that out.
It's top heavy, so it should be infinity.
It's infinity, which, as you may know, is not equal to 0. So the test says, if the limit is not equal to 0, the series diverges. Right? So this actually allows us to conclude that the series diverges. And then we can say by the divergence test. And that would be our conclusion. Yeah, and that's it. That's all you would do, right? And it's again, limits is something you've been doing since Calc 1. The assumption is you're pretty good at it at this point. So taking a limit should be something that you can do relatively quickly. It's going to be, and especially when you know about the certain, we're talking about infinite series. So we're always going to have things going off to infinity. So when you know how different functions relate to each other, you know, like, oh, we know that exponentials are always bigger than polynomials and so on and so forth as you're going off to infinity, you'll be able to a lot of times quickly see whether a limit's going to go to 0 or not, or whether it's going to go to something bigger. And so in this case, the limit does not approach 0. Therefore, the test for divergence says this series diverge, which means there's no need to try to approximate it to something or do anything useful with it because it's not going to add up to anything meaningful. It's going to go off to infinity, right? So it's not worth doing anything else with. This series isn't going to be a useful mathematical object to us. It's essentially a complicated way of writing down the number infinity. So we can move on. Okay. So here's another example. And again, an is just the thing that you're summing. So what we would do here, note, the limit of an is just going to be is the limit of 5 minus 7n plus 3n cubed over n cubed plus 2 n plus 1. What is that limit? Anyone?
Right?
It's 3. Which, as you may know, is not 0. So once again, the series diverges. Running into the other one. Okay, so this is another one. You're expected to be able to take this limit very quickly because it goes to the ratio of leading coefficients. That's something you learn in Calc 1. You have a rational function and you're going off to infinity, plus or minus infinity. It actually doesn't matter. If the degree of the numerator is the same as the degree of the denominator, it just goes to the ratio of leading coefficients. So the only ones who matter is this guy and this guy. And you just take the ratio of the coefficients, 3 divided by 1. So once again, this series will diverge. It doesn't make sense for you to try to do anything with it, do calculus with it, try to figure out what it is, try to write some complicated program to approximate it. It's not going to converge. So we can move on. What about this guy right here? So note the limit of an is going to be the limit of the absolute value of sine n. And what is that? N goes to infinity of sine n. What is that?
It does not exist.
Does not exist. Okay. This guy bounces up and down, right? So sine n, this graph looks like boing, 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 at the level of 1. So it never settles anywhere, does not exist. Now, as you may be aware, does not exist means it's not 0. And so the series diverges. The divergence test or test for divergence. Yeah. Okay. Awesome. So that's that one. So if I'm adding up a bunch of terms that look like that, absolute value of sine of 1 plus absolute value of sine of 2 plus absolute value of sine of 3 plus absolute value of sine of 4 plus absolute value of sine of 5 plus absolute value of sine of 6, going on forever, it's not going to add up to anything meaningful. So we can kind of move on with our lives. All right, what about this one? So here, we will go note the limit of an is the limit 1 over n, which is what? We saw that this was 0, right? So that was 0, right? So what can we say about this series? Based on the divergence test.
It converges to 0.
Okay, so no. Now, that is very important. So this here, this if then statement is a statement, it should be read as a logical statement. So when I say if this condition is fulfilled, then it means this. It doesn't mean you can assume if that condition is not fulfilled, then it does not mean that. So that's sort of a logical thing, because what kind of statement that is. So it turns out if the first condition isn't fulfilled, you can't really say anything about what follows, right? Like, I know if this happens, that's going to happen. But if this doesn't happen, I don't know what's going to happen. That's how you want to think about it. So, but that's actually a very common thing that happens. So I'm very glad you said that, because I do want to deal with this. So there are a couple points that it's going to be important for you to realize. So the convergence of the sequence is not the same as the convergence of the series. So that should be the first thing. And we can see that, we saw that earlier actually. Right? Like if I just looked at this guy and spoke about the limit of 1 over 2 to the n, it was actually 0. But if I added up a bunch of terms that looks like 1 over 2 to the n, the answer is 1. Like the series converging and the sequence converging, they're not the same thing. They do not have the same value in general. So just because a sequence converges to 0, for example, it does not mean that the series converges to 0. Secondly, in the case of the test for divergence specifically, we know what happens if the limit does not equal 0. It turns out we do not know what happens if the limit is 0. And so here, this is actually something I'll put in red, because technically it was kind of a trick question. Not just to be mean, but I wanted to stick out in your minds as this is something you have to look out for. No bueno. There's no conclusion can be made on the basis of this test.
So it's meant to tell us whether we'd be wasting our time by continuing to analyze this series.
Right. That's the idea. And and that's what I mean here by, as its name suggests, right? It's the test for divergence. It can only tell you about divergence, right? So you will never use this test and then conclude, oh, this converges. it means you're not using the test correctly, right? It's a test for divergence. That's the only thing it can tell you about. It's a way to tell you quickly when something definitely diverges. Don't worry about anything else. However, it doesn't cover everything, because in the case where the limit is actually 0, then you would need to do some further examination, right? So here, no conclusion can be made on the basis of the divergence test. So if the limit is not 0, we definitely know it diverges. If the limit is 0, anything can happen. In fact, here, the series, it goes from 1 to infinity of 1 over and diverges. It does, but it's important that you know that we could not tell that from this test. And I'll give you a counterexample. In fact, this diverges. It is a famous series called the Harmonic Series. We'll actually hear a lot more about this series later on, because it's a very important example. It's like one of those examples of 1 over x to the p, where it's the integral of 1 over x to the p, where we actually use that integral to talk about other integrals. There are going to be a lot of series where we can figure out whether they converge or diverge by comparing them to this guy. And we can say, oh, this series is going to behave like a harmonic series, therefore I know it diverges, right? So this is actually a very important example of a series, and it's called the harmonic series. And it shows up in music and analyzing harmonic waves. That's why it actually has that name. But an important example to keep in mind is this, to show you that this doesn't really work. An important example. Or I should say another important example, because you want the harmonic example. Is this series. There's a series 1 over n squared. Now in this case, the limit as n goes to infinity of 1 over n squared is also 0. Just like this one, the limit was 0. But this does converge. In fact, right? So this is like you're adding up 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus, right? So I have 1 plus a 4th plus a 9th plus a 16th plus a 25th plus blah, blah, blah. You're following that pattern, you're adding them up. We actually know what this adds up to. What would you guess that this adds up to? Just take a random guess. Doesn't matter. Just go for it. Be brave. No analysis, just guess. Give me a number.
1.
1. Very reasonable guess. It's like, well, you would think it's 1 and a little change because you're adding up. You already had the 1 here, but you might think that this adds up something very similar to what we saw before. That might add up to 1. You might think 2 but the point is, anyone looking at this, it would be a very reasonable guess that it adds up to some sort of integer or fraction or whatever. It turns out the answer is more obvious than that. It adds up to pi squared over 6. Yeah, I was being sarcastic. In case I need that meme, I was being sarcastic. I don't know if you know that. So yeah, it adds up to something very obvious. Pi squared over 6 is actually what that is. I can add up an infinite number of fractions, rational numbers, and the answer is an irrational number, right? So adding up an infinite number of things is actually, can get weird. But the important thing is for you to know both of these examples as a pair, right? When the limit converges to 0, it tells you nothing. It can either diverge or converge. You don't know. You need something further to tell you. There will be examples on both sides, right? So, so that's the important thing. So if the limit of an equals 0, that alone tells you nothing about the series of an. It can either converge or diverge. We need further tests to determine. That's very important. So the harmonic series is a very important and famous series in general, but it's also one of the most basic series that is used as an example of something where the sequence converges to 0, but the series diverges. And then conversely, a very common example to counteract the mistaken notion that a student might have that, oh, converging to 0 means convergence or divergence or any conclusion at all. The series of 1/n squared is also closely followed with that example. These are examples where both of them, the limit approaches 0, but one converges and one diverges. The harmonic series diverges while 1/n squared, the series of 1/n squared converges to pi squared over 6, in fact, but that's not something we have to worry about right now. But the point is, the right example adds up to something, the left one doesn't. It goes off to infinity. And yeah, you cannot make a conclusion just by looking at the limit is 0. So that's a very important thing about the test for divergence. It can only tell you about divergence. It cannot tell you about convergence. And you have to read the statement in the right direction. Like, if this is not 0, then I know this. If it is 0, then I know nothing. Like, I don't know. Like, I know I need this requirement to get this. If I don't have that requirement, maybe I can get this, maybe I can't. I don't know, right? So it just, it depends. So yeah, so it's very important that you read these statements. And this is in fact true of all mathematical statements, which gets a lot of people in trouble because, you know, in human language, when you're talking to someone else who's a human being and who's not a mathematician or a logician or someone who works with logic all the time, when they say things like if this then that, people usually do assume the other way. Like someone will say, oh, if I study, I'll pass. So, oh, that means if you don't study, you won't pass. No, that's not what it means, right? A lot of people think in reverse because in everyday human language, we kind of, people can say it in one direction and mean the other direction and all sorts of things. But in math, that's not true. The direction in which you're reading the if then actually matters. And if the phrase that follows the if that phrase is false, then the then does not follow, right? You actually don't know what will happen mathematically. So we only know what happens if the limit is not 0. If the limit is 0, we do not know. We have to do another test. There. Okay, so those are some series examples. As you can see, when the test for divergence does actually tell you something, generally it should be relatively quick for you to come away with that conclusion because you know its limits, you know how functions work and you're used to taking limits. You would generally be able to see very quickly whether or not a limit is 0. If you look at a series and then you take the limit of the sequence that you're adding up and the limit does not equal 0, you know it diverges, move on with your life. You don't have to check absolute convergence or conditional. It doesn't converge in any sense of the word, right? If the limit is not 0, it diverges, move on. If the limit is 0, you cannot make any conclusion. You have to do something else to be able to talk about, oh, does it really diverge or converge? So that's very important. So test for divergence. That's the first one. And that's sort of the first one that I want you to think about. We'll talk about strategy, right? Approaching random series and what to do first, what to do second, what to do third. And this is kind of going to be one of the things you do first for any series. In fact, this thing says all series. In the table, it says all series right here. Right? So this is a test that you can do on any series. It doesn't have to have a specific form or anything. And it's going to be one of the first tests that you would try, generally speaking, because it's going to be one of the ones that you can easily come away with a conclusion right off the bat. And that conclusion follows very quickly if the limit is not zero. If the limit is zero, you're out of luck. You have to try something else. And yeah, so here I mentioned what I talked about. So the Sorry. Yeah, so this is a very famous series, the Harmonic Series. Right? It's a nice counterexample to the fact that the converse of the divergence theorem, the converse is what people usually think is false. Right? If A then B, the converse of that statement is if not A, then not B. Sometimes this is true, but most times it isn't. So the converse is false. You should not assume that you can just negate both things, leave it in the same order, and mathematically it still makes sense. The harmonic series is a very important example to that. And it does get its name from music, harmony, harmonics. So if you're interested in, learning more about the harmonic series beyond the class, I gave you some links here that you can actually see as to why it's called the harmonic series and how this series arose and how we know it diverges and all that stuff. We're actually going to do some tests that tells us that diverges, but we actually can't know it from the test for divergence. Yeah, so again, I put in red there, that same warning, right? If something converges, it means that the limit does approach zero, but just because the limit approaches zero does not mean it converges. That is true. And the other famous example is the 1/n squared, which we already dealt with that. Hashtag obviously converges to pi squared over 6. It's not obvious. I was being sarcastic. So that's the first thing. And that's pretty much it. That's all you need to know for the divergence test for divergence. Take the limit. If the limit is not zero, diverges. If the limit is zero, you can't say anything. You have to do something else. That's it. And of course, you have to remember how to take limits to be able to talk about that. Let's talk about the second test. This is called the geometric series test. Took a while for everything to solve. This was actually the first test in the table. Geometric series test. Now this one, when you talk about when to use, notice that it works on series of a particular form. There's another way that this shows up. Sometimes we want to start the series from, say, 1. As most of our examples so far started from 1. And in that case, you just bump the power down by 1. So you would think of this as a times r to the k minus 1. And it's very important for you to realize here that a and r are non-zero constants. Okay. So it turns out if you have a series that looks like this, it turns out that there is a test that you can actually do, and you can know when it converges or when it diverges. And in fact, I do want to mention here that the convergence in this case is actually absolute convergence. not all tests gives you absolute convergence right away. So the geometric series test does it, so does the ratio test and the root test. I mean, they're down here, the bottom of the list. See that they make talk about absolute convergence. So yeah, but the geometric series test can't actually tell you about absolute convergence. Whenever the geometric series test tells you something converges, then it converges absolutely automatically. Now, let's actually talk about the geometric series test. So a geometric series is the sum of the terms of a geometric sequence. And it is a series of the form blah. So this is what's called a geometric sequence, right? It has to do, the name has to do with the geometric mean. If you want to talk about, you know, where that name comes from, you know, why is it called geometric? I gave you a link here, so you can actually explore that if you're interested. You don't need to know. But yeah, I did mention here, this is very important to realize. In the above, A and R are non-zero constants. A is called the first term because when you start writing out these series, this is what it looks like. Right, so that is A will always be the first term for that series. When you plug in this case, if you plug in n equals 1, you'll get r to the 0 and you just have A. In this case, if you plug in n equals 0, you would just get r to the 0, which is 1, and then you just get A. So A is the first term. Okay, R is called the common ratio. It's called the common ratio because if you take any term, divide by its previous term, you'll always get R, right? Like, so if you take anything that looks like R to the n plus 1 and divide by the previous term, AR to the n, you just get R as the result. So this is a common ratio. Right, so if you take the ratio of successive terms by taking this guy and dividing by the guy before, R is always the number you're going to get. Essentially, this is a series where the terms follow this pattern. You start with a number A, and then you keep multiplying it by R, right? So you have A, that's the first term. Then the next term is A times R. Then the next term is AR times R. Then the next term is that times R. Then that times R. So the powers of R keep going up because you keep multiplying each term by R to get the next term. And so you're repeatedly multiplying by R. And so you get the successive ratios is always R, because for every term you multiply by R to get the next term. So if you divide them, you just get R back. And so R is called the common ratio. So this is called a geometric series. And it turns out whenever there's a series in this form, we can actually know what it will add up to. And there's a legendary story. I don't know if it's exactly true or not. It's probably more myth than reality at this point, of a famous mathematician by the name of Carl Friedrich Gauss, German mathematician. He's considered to be one of the greatest mathematicians of his time. And there's a story how about when he was small, you know, he was in school, he was like 4 years old or whatever, you know, preschooler, and you know, him and his class are just being noisy. The teacher got upset with him and was like, "Hey, everybody be quiet. I want you to add all the numbers from 1 to 1,000. Yeah, right." So these are like, you know, like little kids, 4 years old, 5 years old. They're just learning how to count with pebbles. The teacher thought, all right, I give them to add up all the numbers from 1 to 1,000. They're going to take forever to do this. I will have quiet for the rest of the day as all these kids try to figure it out. Unfortunately, Gauss figured it out in a couple of minutes, gave her the answer. He's like, okay, can I go back and play now? Right. And that's how the story goes. And the legend goes that he used a trick that's actually very common, and we're actually going to use it. So I actually want to show you what that trick is here was his idea. He's like, all right, I'm not going to actually add up the numbers from 1 to 1,000. That's crazy. But suppose S is the sum that I want, and I know that's 1 plus 2 plus 3 plus going all the way up to 1,000. Now, little baby Gauss knew about the commutativity of addition. So he's like, well, I would actually get the same thing if I added all the same numbers, but in the opposite order. And here is what he noticed. He's like, well, if I added this, like add this plus this, I would get 2s. And then if I add this plus this, I would get 1,001. Add this plus this, I get 1,001. Add this plus this. Oh, look at that. There's a pattern. You get 1,001. And you do it all the way up to the end. You get 1,001. You get 1,001 all the time. And then you're like, oh, but there's 1,000 of these guys. There are 1,000 of these. So it turns out that 2s is equal to 1,000 times 1,000 and then 1. And so the original sum is just going to be 1,000 times 1,001 divided by 2. Or it's actually 500 times 1,001, which is 500, 500. So 500,500 is what you would get if you added up the first 1,000. If you add all the numbers from 1 to 1,000. And that led to, by the way, something else you saw in Calc 1, that the sum of the first n terms, if n goes from 1 up to k, then that adds up to k times k plus 1 over 2. And you actually did that when you were evaluating like Riemann sums. You probably did it with eyes, I think, to kind of make it look sort of like the formula you would have remembered from calculus. Usually it's something like I goes from 1 up to n. It's n times n plus 1 all over 2. Right? This was something that you proved, and this is where it came from, right? If you plug in n equals 1,000, like that's it, 1,000 times 1,000 plus 1 all over 2. You can actually play the same game. Just think of this as the 1,000 as n. All these guys will add up to n plus 1 individually. There are n of them, so it's n times n plus 1, and then you divide by 2 to get the sum. So you can actually figure that out. Now it turns out you can actually you can actually do a very similar trick when it comes to the geometric series to actually figure out what it adds up to. So we know that it should be the, we want to do the sequence of partial sums idea. So let's actually look at what that would look like. What would this guy actually look like? So if I add up the first n terms, that would be a plus a times r plus a times r squared plus going all the way up to a times r to the n minus 1. Now, we're a little sneaky here. We multiply by r. And turns out that you would have a times r. Everything kind of gets shifted. A times r squared. A times r cubed. So this will go up to a times r to the n. And you can actually do a very similar trick here, where what we would do here is actually subtract them. So if I think of this as equation 1, that is equation 2, I'm actually going to compute equation 1 minus equation 2. So what we would get here is 1 minus, that's weird. I would get 1 minus r times Sn. And if I subtract these, it's kind of like a telescoping sum. This will cancel this will cancel this will cancel that. Goes all the way up to this canceling that. And so what we end up with a minus ar to the n. And so from that, you can see that Sn is going to be a times 1 minus r to the n all over 1 minus r. And so you can use our definition, the sum that's just going to be the limit as n approaches infinity of Sn. Well, that's going to be the limit of a times 1 minus r to the n over 1 minus r. Now, the only thing that has n in it is this r to the n, which now you want to think about what will actually happen. And remember, your r is a constant, and you're raising it to the nth power. Now, this tells you that if your r is actually bigger than 1, then that's going to go off to infinity, right? Because you're taking something that's bigger than 1 and you're raising it to a positive power. That power is going off to infinity. If your r is within 1, it's less than 1 within absolute value, could be a little bit negative, but smaller than 1 in absolute value, then it goes off to 0, and this actually gives you a number, a over 1 minus r. If your r becomes too negative, like minus 5, again, you have the same issue. You have minus 5 raised to the nth power. It grows big and everything blows up. Obviously, your r cannot be equal to 1 because you have 1 minus r in the denominator, and that's going to divide by 0, and that's going to mess everything up. So now you actually know that this will actually give you an answer only if your r is smaller than 1 within absolute value. So that way, when you raise it to power, it gets smaller each time. And so this gives you 2 scenarios. So either you get a over 1 minus r if it converges, and it will converge if r is strictly less than 1 in absolute value. Otherwise, it will diverge. And so that leads to the geometric series test. Given a series of this form, your a and your r are non-zero constants. The series will converge, and it will converge absolutely. And it converges absolutely because we can put our r in absolute values and it's not going to change anything. Right? If I put in absolute values around each term here, I can factor out the a. It's still going to give me the same idea. Whether the r was positive or negative doesn't actually matter. It doesn't matter if it's positive a half or negative a half. If I raise that to the nth power and n goes to infinity, they're both going to give me 0, and the answer is going to be the same. So you actually have absolute convergence, and that's actually something I do want to emphasize. You get converge absolutely. And on top of that, you know exactly what it converges to. It will converge to a over 1 minus r. And that kind of tells you where this thing in the table comes from, right? Tells you that the series converges to a over 1 minus r in that scenario, and it diverges in any other scenario. And when it converges absolutely, because you put your r in absolute values, it doesn't matter. The a is just a constant multiplier. You can always factor that out. We know that from our series properties. And so you have this idea. And so a geometric series is any series that can be written in this form. And so I have a bunch of examples here where we can do, and we can figure them out with geometric series, and I have some other tests here as well, but we'll deal with that later. I'll deal with this one very quickly though, because you might remember this guy. This is the guy from the dichotomy paradox, right? 1 over 2 to the n, and we're adding those up. This was when we had 1/2 plus 1/4 plus 1/8 plus ... This was guy before. It turns out that you can actually think about this as a geometric series. Notice that this, you can think of this as 1/2 times, well, this guy, 1 over 2 to the n. You can think of this as 1/2 times 1 over 2 to the n minus 1. Or in other words, 1/2 times 1/2 to the n minus 1. And so this guy is like your A, this guy is like your R. So this is the form AR to the n minus 1 when your n is starting from 1, right? So you can look at this guy and you can realize, oh, and you can know that from this pattern, you keep multiplying by 1/2. To get each new term, right? You start out with 1/2, you multiply by that by 1/2, you get a quarter, multiply that by 1/2, you get an 1/8, multiply that by 1/2, you get a 16th. You create this list by just multiplying by the same thing over and over. There's a first term, which is 1/2, and then you're multiplying by the common ratio, which is also 1/2. So it's like your A and your R are both 1/2. So you can actually conclude. So this you can think of as, this is just a series, n goes from 1 to infinity of 1/2 times 1/2 to the n minus 1, which is geometric. So you know what it converges to, A divided by 1 minus R, which, hey, that's 1. So we saw another situation in which this actually gives us 1. So yeah, and you can think of it as a geometric series. So we will stop there for tonight. There are other examples here and some other notes of other series tests, which we will get to next time. But we'll stop there for now. We'll pick up here tomorrow. As I mentioned, so tomorrow the test will come live at 3 p.m. and be live until like the following day around 9 p.m. And tomorrow's class, I will pick up right here where we left off. I'll teach for 2 hours. If you guys have questions after that for the last hour, I'll answer them. If not, I'll just continue because we'll just keep going. But we will stop. We'll stop there for tonight. So thank you for your time and attention. And that's it. You guys have a good night. I'll see you guys in the next one. Ciao.